Hello, I am Vinson Jones. I'm a graduate student at the University of Arkansas. Today I'm going to go over one of my research topics, the development of a stackable switching position for use in multi-level converters. Interest in medium voltage converters for the distribution system has been increasing over the years. Here is an example of such a converter. These converters can be used for energy storage and current compensation. To achieve medium voltage levels, multi-level converter topologies have been suggested. An example of a multi-level converter for connection to 15 kV class distribution systems is shown here. This particular topology is the flying capacitor converter, which consists of submodules formed by a capacitance and half-bridge structure. Take a look at the first submodule. To maintain 2.4 kV voltage, a 3.3 kV switching position is required. Currently, 3.3 kV semiconductor devices are not readily available commercially. This means high cost and lead time and availability risks for the manufacturer. Alternatively, the use of lower voltage devices in series to form an equivalent switching position has been proposed. These devices can be cheaper and are more likely to have more than one source. However, voltage balancing among these devices is required. So, in developing a stackable switching position, this was an area of importance. Here, a switch with the chosen voltage balancing circuit is shown. For simplicity and reliability, it only consists of passive components. With C sub A charged to the nominal off-state voltage of the device, any overvoltage results in the current shown, charging C sub B. When C sub B is charged, the resulting current shown here increases the voltage at the gate of S, turning it on. This saves it from an overvoltage condition. Here, the turn-off and turn-on transients of two series-connected devices is shown with an inductive load. The voltages across both of the devices S1 and S2 are shown along with the inductive load current. In both cases, a destructive overvoltage is avoided by forcing the OFF device into the saturation conduction region. Another issue with high voltage, high dVdt switching transients are the resulting common mode currents due to the common mode capacitance of auxiliary power supplies. An abstraction of the common mode capacitance of auxiliary power supplies is shown here on the right. One common mode current path is shown in red. This current, along with the trace inductance, can cause corrupted IC signals, and the resulting partial discharge within galvanically isolated supplies can deteriorate the magnetics over time. To avoid these phenomena, a self-powered circuit was created to allow the switching position to provide power to itself. This eliminated the common mode capacitance and the resulting common mode currents. During the off state of the switch S, C sub R charges to the nominal off-state voltage of S. When S turns on, the inductance L sub R is charged by C sub R. This energy then resonates into C sub GD, which is in turn used to power the gate driver and other auxiliary circuitry. Here is a waveform showing the current through L sub R and the voltage across C sub GD. To power the switch at voltages below the nominal operating voltage of the switching position, a startup circuit was created. This circuit, along with L sub R and C sub GD, form the equivalent of a buck converter, enabling the switch to power itself at any voltage. Simple open-loop control using a lookup table or curve fitting can be used to modulate the duty cycle of M sub AU according to the voltage across the switching position. Combining the voltage balancing circuit and the self-powered circuit forms a stackable switching position which can be employed in multi-level converters. These circuits were built on individual PCBs and stacked to form the final stackable switching position shown in the bottom right. Here, the switching position as installed in an 11-level flying capacitor converter is shown. Thank you for joining me for this overview of my research.